I'm Alan Weisberger, the creator and chairman of the IEEE Silicon Valley History Committee, and we're very pleased to be here at the Ethernet Tech Summit with our new partner, Lance Leventhal. Lance is the program director of this conference and Conference Concepts, and thanks to his efforts, we have this wonderful session. With your support. And we look forward to further events with Lance at the Open Server Summit and the Flash Server Summit coming up later this year. I'd like to recognize some of our officers. We have our hospitality physics expert, Francine Belson. Want to stand up, Francine? We have our member at large, Paul Wesling, who is our cameraman today. Thank you, Paul. And we have our own Jeff Thompson, who is moderating this discussion with Larry Roberts. Jeff has been a strong contributor to IEEE for many decades. He's been the chair of the IEEE 802.3 Standards Committee. He's been on the IEEE Standards Board, major contributor to IEEE ComSoc as an attendee and panelist, and he's organized an event which he chaired last April for the IEEE Silicon Valley History Committee on the history of wired LAN competition. So we're very pleased to have him as the moderator and interviewer. At this time, I'd like to introduce Christos Kallios, who will talk a little bit about Larry Roberts.
All right, so I have the distinct and honor to introduce Larry, whom I've known for more than 20 years now. He's been quite influential on my PhD thesis, and I know him from the ATM years. And then I had also the pleasure to work with him at Casper Networks when he started Casper Networks back in 1998. I won't go over Larry's extensive and really impressive biography. I believe that everybody knows about Larry. Those of you that don't know about Larry, he's a true father of the internet and really visionary. When he started, he's been very instrumental in creating the internet as a research scientist out of MIT, and then as a chief architect and the director at DARPA, the Department of Defense. So he helped essentially starting the internet. It was called ARPANET. At the time, he provided the funding and the architecture for the internet. A few tidbits about Larry. He has actually done the first, he has written the first email application or program. It was used to be called back then. He's been very instrumental in writing the first routing algorithms and also the wireless access schemes, the AlohaNet, for those of you that are like old enough to remember that. So when it comes to technology innovation, he's a true trailblazer. At some point, and interestingly enough, in his career, he was the CEO of DHL, which is a logistics and shipping company, something similar to FedEx, essentially. And you may wonder what's common between a shipping company and the internet. Well, they both have to find the best route to deliver your packet, and that has to be done without any loss, all right? So one of the things that has really amazed me about Larry, and I know him again for years, is that how he would command Excel to solve real complex queuing problems. I mean, this is really fantastic, the way he does that, and I've actually never told Kleinrock about that. So he's definitely a brilliant mind, and I always say that if he was in the field of biology, perhaps he would have found the cure to cancer already. Actually, both his parents had PhDs in chemistry, so obviously he's in the wrong field. Of course, the dilemma here is that which is more important, right? Is it cancer or the internet? So with that, please join me in welcoming Larry.
Good afternoon and welcome to our Fireside chat. I was asked yesterday about the fireside aspect of the presentation. Not knowing whether or not there would actually be a fireplace, I came equipped with the minimum amount of equipment to make the fireside aspect the truth. My experience has been on the Ethernet side of the internet. I started out the confluence or the integration between early Ethernet and early ARPANET was a big factor. And I'm delighted to finally get to meet Larry, and it's a pleasure to be with you here today. I'd like to cover a little bit of everything today. I'll scan through the list and then we'll start over. The dawn of packet switching in an environment dominated by circuit-switched voice networks. Then how you got from that to the early issues that faced you, then the explosive growth of the ARPANET, and how usage changed from terminal host to basically file transfer things, moving from the research domain to the commercial domain, the great ATM experiment, then coming forward to the big problems that we have now and long term, and then at the end I'd like to go back and try to figure out why it's such a big success. And the other thing that I want to throw on to the list that I didn't have written down is to talk a little bit about X25. So let's talk about how the whole business started and what the environment was at that point in time.
Well, the first time that I started working on the network technology was after a meeting at a computer conference with Dr. Licklider. And Dr. Licklider and Corpito, who ran the MIT Mac program, and I were sitting there, and Lick was saying that the next real challenge is to build a network to connect all the computers. And he's written papers on the galactic network at that point, but it wasn't that those papers, it was more just talking to him that gave me the feeling that, yes, there was a big problem. I was having problems myself because I was running the Lincoln Lab TX2 facility, which is the biggest computer around at that time. And Marvin Minsky at MIT, running the AI lab, was anxious to get photographs that I had scanned into the computer. There weren't many ways to scan things at that time. I had taken an old fax machine and redesigned it for the computer. And
so was this within the context of the computer room itself or more remote?
No, this was in the, MIT was down the street, a long way. But the point was, in the lab, I had already scanned the photographs. I had lots of photographs on the computer. And to get them to some other incompatible computer, which was, in fact, almost a copy of the one at TX2. It was a PDP-10. Still, it wasn't compatible. So what happened was I had to buy an IBM tape unit that was compatible with his, do all the hardware connection to connect it to the computer at TX2, make him a tape, and bring it back to MIT. It was a very, very long process. Not very easy to move files at that point in time. And that's what was in the back of my mind when Lick talked to me, that we really couldn't move stuff that was unique and on some computer to get it to people around the world and on other systems. It was too much incompatibility in the various systems.
So at that point in time, were you thinking about tape system compatibility or communication system compatibility?
Oh, communications, because I wanted it to happen instantly. I had already worked on the communications part of it by attaching a telephone line directly to Armour Bowe's house so we could figure out the spectrum of his living room so he could build his speakers. And that put me into the place where I had telephone lines connected with ADD conversions and I could work the communications. But after that, I undertook to do an experiment, which ARPA funded, and that experiment was to connect the SDC computer to the Lincoln computer and see if we could see whether the computers were a problem the communications and what kind of communications we needed. I used a dial-up 4K kilobit dial modem, which back in 65 was about the best you could find. And
I'm actually surprised that it was that fast at 65.
Yeah. Anyway, the problem was it was extremely unreliable, and the telephone network had all sorts of static noises from the old relay switches in the same offices that the cables were going through. So it really dictated the size of the packet. So I adjusted the size of the packet based on my recording of all that noise to where a burst would kill a whole packet, and so I was almost 1-for-1 with packets. And the result was you had a relatively short packet at 1,000, well, it was less than 1,000 bytes, but it was short.
And so during that era, that was right when AT&T was introducing T1 circuits, but not...
No, it was earlier than T1, but
not on a basis that was accessible to subscribers, is what I was going to say next.
Yeah. And in fact, whatever was available was nowhere near as economic as what I did start with, which was 50 kilobit using 9 telephone lines and a huge modem that they had. But under the Telpac tariffs, I could afford that. It was relatively reasonable for DoD. In any case, I designed then what I wanted to do about the network. I knew what I wanted to do. Kleinrock was my office mate, Len Kleinrock, and he had done all the queuing theory, so I knew that we could do it and the queuing would work, which was critical, because if we didn't know that, both AT&T and the Defense Communications Agency told me I was crazy because it would never work because all the packets would fall on the floor. And as it did with paper tape almost. With the paper tape you could pick up and put back in.
AT&T kept saying, you can't do it over our facilities, they're not good enough.
Well, there was another factor too for AT&T in doing it, and we'll come back to that later on. But the issue was I needed to have the packet network work so that it was fast, live all the time, because you can't wait to dial up, and has high reliability and high speed because the computer was only sending 1/15 of the time. In other words, we measured it between the two computers and all of the activity, which was that we found that they sent about a burst, and then they waited 15 bursts, and then they sent something else. That was extremely inefficient on a circuit switch.
And how big were those bursts?
Those bursts were maybe hundreds of packets, but they didn't. But because you were sending a matrix or a few other things. A lot of what I was doing with SDC was using their matrix math and mine in various different ways. So in any case, I concluded that we needed the network to be built as a packet network, and that was my report. ARPA tried to hire me to do this, but I kept on refusing until Ivan Sutherland left, and he had been trying, and then his deputy, Bob Taylor, took over. And he went to Hertzfeld eventually after I'd said no for a few more times because I didn't want to go into management. And then Hertzfeld called the head of Lincoln and said, we have 51% of your funding. We'd like him down here. And the head of Lincoln called me in and said, it will be in your best interest and ours too for you to do that. And if you have any problems, we'll take you back instantly.
Excuse me.
And we'll pay you until they pay you. So it was it was simple. I then moved to Washington and did the ARPA task. The work was handling all of the research in computer science, which is a whole bunch of universities that we were funding, as well as undertaking the design of the network. In any case, the result was I designed the network and
Excuse me, folks.
gave a paper on it in '67 at Gatlinburg, where I met some of the people from Donald Davies' group in London who were also thinking about packets, and they mentioned Paul Barron's work, which was actually in the safe in the office because it was classified, but I hadn't read it or seen it.
What was it about? Did you ever find out?
Oh, well, it was his attempt to look at a secure voice network using packets, or something like packets. The word packet came from the group in England. But I switched as soon as I heard the term packet because it was a much better word than message. And a message was the full thing rather than the piece.
And you were talking about error performance. So that drove early decisions on packet size?
Right. In fact, packet size didn't change very rapidly over time until we finally got jumbo packets, because it basically was all 1,000, few hundred bytes to begin with, and then up to 1,000 or 1,500. In fact, that's what most of it is today. In any case, I then designed the network, had RFP produced with help, and went out to, first met with the universities at one of our annual meetings and told everybody they were going to join the network, like it or not, and their funding would be depending on them joining the network and doing experiments. Most of them didn't want anything to do with it because they thought their computer would be overused by other people.
So the attraction of getting access to other people's computers wasn't enough of an attraction to overcome their fear of letting somebody else into theirs.
Right. It turns out, for example, one of the problems was both artificial intelligence groups, McCarthy at Stanford and Minsky at MIT. They both didn't like it for that reason. But on the other hand, they soon found that collaborating on papers was extremely valuable. So, in fact, so we started the network, gave the contract to BB.
And starting the network involved precisely what at that point?
Well, I had to go out on RFP to find a vendor who would build the switches, the routers, if you will. We called them IMPs. And that was given to BBN because they actually had the best proposal and the best structured team. People have argued that may have been because I knew them. No, it was really because the team structure was much flatter, and I hated big vertical structures with too many managers up above.
And then what did the initial rollout look like?
Well, amazingly, the job got done in 9 months. I haven't seen many software projects finished in 9 months lately.
Memory was small. You couldn't write very many lines
Yeah, I
of
had
code.
4K of memory, which was certainly not very much. That was a huge limitation and made it that we couldn't do as much as we'd like. But
So at 4K, this was all still core memory, of course.
yeah. Well, there were disks, but
Right.
the core
Resident memory was all core.
was very small. So that got built. We did the first installation at UCLA in 69, and then 3 other locations on the West Coast, and that all worked extremely well. That story's been told a lot of times by UCLA of how it came up, and the first message was LO for login, but then it failed.
2 out of 3 isn't bad.
So in any case, that got fixed quickly and everything went forward. The majority of the traffic at that time was experimental, and a few things like the paper activity I talked about, sharing papers, but most of it was terminal to computer so that people who came on the network and didn't really have a big allocation at their site could go to other sites where we could provide computer power. So they actually just were using it as a long-range access.
Now, initially, it wasn't actually spanning time zones. That came a little bit later, but not much.
But yeah, the next year.
Yeah.
It wasn't long. And then by 71, the network actually was operating effectively throughout the country, and we had the whole, I forget the number, 20 nodes or so.
And then,
And then basically, we started email. Tomlinson came up with the apps that we had asked for, which was basically send and receive. And that wasn't terribly useful by itself, but I took a text editor and wrote an app which put it into all the things we see now in an email routine. Save this, respond to this, whatever. And
But this was basically a file transfer protocol that was doing an entire mail at a time.
right. Now we had mail transfer. That was the routines that got finished by BBN and Tomlinson. And then we started seeing huge growth in email traffic because that was immediately useful to all the people communicating with everybody.
The killer app.
Well, it was at the time.
Yeah, no, certainly.
And since the text editor I used everybody had, that spread instantly, although people wrote other versions. But it was basically very easy to duplicate. So in any case, email took off the network and probably was the dominant traffic for a few decades on the ARPANET, which went on.
So how did the ARPANET then tiptoe into, I can't quite say the commercial domain, but out of the academic and
Well, there was two transitions. First of all, my plan actually was in my original statement of intent to ARPA, because you write plans.
Yeah.
I said we're going to get rid of it after the research phase and turn it over to somebody. I tried to. I went to AT&T and I said, how would you like to just take it over for free, expand it for commercially, and have us pay for the access, not the trucks. And they said no. It's incompatible with our thinking. And it was a free gift. I mean, it would have been an immediate service.
Do you remember who it was that said no?
It was a very large committee of all of their executives plus the Bell Labs people. And some of them, they have had the other opinion, but most of them had the opinion this isn't our business. And as I said, there was an extraneous factor that there was an antitrust agreement between them and Western Union, and they didn't want to get involved in that either. I don't think it would have had that effect, but it was.
Well, they certainly had their own large teletype network,
Yeah,
as well as Western Union, so I can't see how that would have been an issue.
I don't think it really was, but they didn't have it. In fact, after we, I'll come back to them later on. Well, that was the first step. The second step was I left in 73, started Telenet, and Telenet was to build a commercial network. The first thing I did was write a host interface protocol so that somebody could connect to it without the unique things that ARPA had. And that was X25. And that proved to work. And working basically was sufficient for selling the standard. I went to CCITT, which is the ITU now.
And so, at least in the US, this was all based on leased lines from AT&T.
Yes. Yeah. Well, I mean, it could have been from anybody after
right,
that, but it was.
They had them. But you provided all the switches.
We provided the switches and the lines.
Yeah.
And actually didn't charge people at that time because it was a research activity. But then, since I couldn't get AT&T to take it over or anyone else, I went to the FCC, Bernie Strasberg, and I said, okay, what do I do? How do I get this going? He says, we'll start a new carrier because that's in our charter now. Mm-hmm. MCI had just started and we knew that kind of thing would work. So we started Telenet. And Telenet became a carrier under the current laws that everybody's arguing about with the recent change. It turned out to be very valuable to be under that law because you're totally protected from any lawsuits. Nobody can sue you for damages outside of the money they paid you when it didn't work.
So can you go a little further about how the X25 TimeNet business developed and then got handed off?
I started X25 and CCITT, and we already had it working. So Telnet operated immediately, was already operating in 75 by the time it became a standard. It was the standard, and it was the international standard until the mid-90s when the internet took over my original activity. So it turns out that X25 is still running. It is in fact, still used for financial transactions because it's more reliable and easier and still works tremendously well. But it was never upgraded in speed as things went forward.
So what's the maximum speed that can be supported
Well,
with X25 these days?
I don't know whether anybody's gone faster, but 50 kilobits was what it was designed for. But it could have been expanded to T1 and T3 and so on as time went forward. We certainly have the hardware capability to do it today, but it wasn't done because people figured it was too hard. And so let me come back to what happened to the internet. Basically, during that same period, I turned the office over to Bob Kahn, and he hired Vint Cerf. And they worked on the concept of TCP, published that back in 73, when I was still there, and the word internet, which they coined. And then the result was they kept on expanding that for a number of years, even though I couldn't get it sold and I left. But the government still wanted to get rid of it as a research net, turn it into a commercial net or an operating net. So it was split into two pieces by them, and one went to DCA, Defense Communications, and one went to NSF. And NSF then undertook to upgrade it to T1 and higher speeds. And by the early 90s, MCI had started MCI Mail, and which was commercial, and shortly after the network was allowed by NSF to go commercial. So it basically evolved into the commercial net we see today with many different carriers operating different pieces of it. So that was back then. It grew extremely fast during that period. In '83, when we switched the ARPANET from NCP, the protocol that I started back in the origination of the network, to TCP IP, it was that happened in '83, and in '86 the TCP IP started collapsing because the network didn't have anywhere near the capacity that many users used if there was no congestion control. So we had a rash of activity in the IETF by Jacobson and others to improve the protocol at the host end so they could talk across the network without losing everything to congestion. And that was an amazing set of things. If you look back today at where all the work on the internet protocols was done, it was back in the 80s and early 90s when they still were using the 50 kilobit and then T1 lines. They weren't thinking of 100 gigabit cables and trunks, which today you couldn't come close to filling with one flow. A TCP flow is stuck at megabits, not gigabits.
And where in that evolution did they pick the address size for IPv4?
Well, address size was an interesting thing. The first NCP had a very small address size of 256 computers. X25, we expanded that to the international standard X1, I think it was, that had 121, yeah. So it had all the countries, and each country had a number of carriers, and each one of them had a large address space. So there was quite a bit of address space, bigger than TCP IP has, IPv4. But it was like 40 some odd bits rather than 32. But then you needed higher speed cables, and people went to doing it with TCP, and the result is that it didn't pay attention to the distance, and we now have a problem with TCP over long distances, but we'll come back to that. What was the question?
I don't know. You were doing swell with that one. We're having a good time. I think asked about the address size.
Oh, the address size after that.
At the
Well, of course,
transition point from ARPANET to Internet.
well, TCP went immediately to the 32-bit addresses that we're using today with IPv4. And unfortunately, we didn't believe at that point in time, and I was certainly part of that didn't believe it was feasible to build either the hardware or the software to handle variable length headers very well. So it was all fixed length addresses in the thing. If we had done a variable length address, we never would have had to go to IPv6, which is still a huge expense facing us.
But at that point in time, Ethernet and XNS were already at 48-bit addressing.
Yeah, lots of things had larger addresses. But of course, this was decided back in before '83, so it was early. And it looked like it would be sufficient for the computers in the world, not all of the devices, not the IoT.
Moore's Law.
Well, actually, I make a comment about Moore's Law. Moore's Law was published 2 years after I did a study where I predicted 18 months as the doubling time for computer technology. Moore did it from the semiconductor thing, and he had a factor of 2 in his first prediction. That was wrong. He went back to 18 later. My 18 was wrong, as I figured later on, as I recorrected, because I had included a version of the Iliac 4 that never happened. And if I had left that out, it would have been 20 months, which is what it has been for a long time.
18, 20, 24, who cares? My theory is that it actually works going backwards also, back into the 19th century.
Oh, really?
If you go back and look at the Marconi stations that were built turn of the century, they were power plants where they switched the armatures on generators and just sprayed static into the air. And so they fit on the curve.
Well, the reason I did this study was because the DoD was leasing computers or buying them and holding them for 10, 15 years and thinking that was economic. I wrote this paper to show them they ought to turn them over every few years.
Well, at that point in time, they were confronted with the fact that the largest computer in the world, the AT&T switching system, was based on a 40-year write-down.
Yeah, and they had trouble with that too.
Oh, they did. But that was their economic model. Yeah. And bound into all their rate structures, so very, very difficult to change.
In fact, when Telenet was bought by GTE, I then moved into GTE's superstructure and learned about the way their finances work. And their finances, like AT&T's, were negative cash flow, all funded by bonds for their equipment. And I couldn't figure out how you ever get out of that. Very difficult. Of course, wireless has gotten them out of it.
You weren't supposed to get out of it. Phone companies were supposed to last forever.
Yep.
Okay, let's talk for a couple of minutes about just what happened when the ARPANET went commercial and the early explosion of that. And then after that, I'd like to talk about ATM for a few minutes.
Yeah, okay. Well, first of all, there were 2 high-growth periods in the Internet's history. One was in '83 when everybody switched to TCP, and they had primed everybody and made them work for years to get that to happen at that point. So traffic picked up quite a bit at that point as more computers came online. The second one was when it went commercial in '93 approximately, and it became available to everybody, and then it grew extremely rapidly, but actually quadrupled in 1 year. that hasn't happened since, but in fact, there was huge arguments between various ones of us who were tracking it. I had the government data, so I knew what was happening, and I also was polling all of the providers, so I knew what they were doing under NDA. And so I knew it was quadrupling in that year, and I wrote about it, and other people said, this is crazy, we're seeing it externally. It's not more than a factor of 2. But in fact, that factor of 2 was pretty good average over the first decade or 2.
And
per year, I mean.
ATM.
Well,
how did it start, and how
actually,
did it strangle?
ATM was an important technology from the point of view of being able to do this a lot faster and a lot quicker with a hardware environment.
And it was supposed to be the first great convergence play, right?
Yeah. Well, it turns out that many mistakes were made. And one of them was the extremely small packet size, because that's what voice had to be theoretically. Today, that wouldn't matter because the trunks are faster. But it was a problem that was never fixed then. I, in fact, voted to change a number of things in the ATM forum, and they didn't happen. The second was that the computing capability was way too small compared to what we needed to do packet switching. If we were going to handle the kind of things that the internet handled, it wasn't big file transfers like video, it was shorter things. And so it was bifurcated to where ATM was only good for the big, long transactions. It had to use a packet switch router in addition to that to then put it all into a trunk to get it somewhere into one ATM stream. So it and/or frame relay were basically not going to solve the problem of replacing IP. And so it actually died out with time. There was a second problem with it, and that I saw as well, and that is we spec'd it so tightly and so completely that any company could go build it. There were no secrets. And so everybody did. And the competition was broad, and margins were bad. Whereas
from the outset.
Right.
There was never a profitability period.
Right, there was never one. So that was what happened with ATM, and the big change there was ABR, which I worked very hard on, and that was the protocol that allowed us to achieve a quality of service over the link that was guaranteed at a very high level. That was lost. It's still being used in places. In fact, I've been talking to my son who lives in New Hampshire. They get their local service over ATM because that's the only way they can deliver voice to the small customer at a lower speed. But it's just for the local access link then. So people still use it for some things, but it's certainly not the basic thing we thought it would be.
Not an external interface.
Right. Well, ATM had its day. In fact, there was all sorts of work I did in one company on it, 2 companies I worked on it, and then concluded it was the wrong direction.
I know my company used it for backplanes for quite a while. So it was supposed to be the great problem solver with respect to Ethernet, because Ethernet was, quote, so inefficient. I always wondered if you couldn't have taken care of 80% of those problems by just locking Ethernet down to only 2 packet sizes and having dual paths through a router. You have a big packet and an acknowledgement size packet. And then
Well, you could have done it with Ethernet, but we didn't.
yeah, no, that's right.
And in fact, IP routing is very different from what Ethernet got into, and probably excuse me, kill everybody. Probably one of the real reasons why it didn't shift.
So, what are the big problems we have to face now and going forward? Certainly, the environment has changed enormously with growth and with the integration of so much wireless service on the edges of networks.
One thing I didn't mention is one of the projects I started at ARPA was the packet radio terminal, and I in fact wrote a paper back then, which I've just been trying to put together copies of on my website. But in any case, I had a picture of a small handheld terminal, much like your phone, and it basically was in order to use the technology we were developing with AlohaNet for local wireless. And we did that here in the San Francisco area way back in the early years. Actually, Bob Kahn took over the project from me and continued and made it complete. And that was the underlying basis for the cell phone activity.
Was it more scalable than AlohaNet would have been?
Well, I mean, one of the protocols, I mean, I wrote two papers at that time. One was slotted Aloha, which was twice as effective as Aloha. And the other one was guaranteed bandwidth over a satellite, which also worked for cellular.
Yeah.
And where you could, once you had Aloha to find your access place, you can arrange for a stream. So you had both. And actually, ARPA did that with the satellites as well. There was one thing that was going on through all this period that I want to come back to answer where you're going, and that is protocols in general. What I did was I started packet switching, and I built the first packet net, and I made it. I knew that the economic advantages, there were 15 to 1 already, and they would grow over time.
So just for context, the baseline was that against circuit switched and
Yes.
streaming protocols, or
Well, I mean,
continuous connection protocols.
actually, what I realized was that for voice, you're using the circuit a third of the time. Mm-hmm. For video, maybe half the time. But for most data, it's way below that. And even for those two, it was still economic to not have to have the other channel or as a wide a bandwidth in the other channel. So in fact, so it was compared to circuit switching. But
so is this basically a comparison between dedicated circuits and statistical multiplexing?
yes,
Yeah.
basically that. In fact, if you didn't share the circuit, no one person could use it, and you'd have to have an extremely fast circuit switch, which could be built today. In fact, people tried. Back then, there was one that got started about when Telenet did, and it failed quickly.
Well, and that's, I believe, the basic underlying problem with optical switching.
Yeah.
And optical networks is there's circuit switch networks, and the switches just aren't fast enough.
Well, and you don't have enough to send at any given point in time. In any case, where we're coming to, well, let me go through the protocol history first, because NCP, which was there in 71 or 69 to 83, that protocol basically stopped at each location, allocated packet buffers back through the network to the previous one, and checked the packets for some check. And if they weren't correct, went back to the previous node and got a copy. So across the network, you were guaranteeing a reliable service.
But on a hop-by-hop basis.
On a hop-by-hop basis, which, if you think in terms of what we then went to with TCP, where across the world we have to do it in one hop, and if anything's wrong, we have to go across the world to get a copy, it takes dramatically longer than the original protocol. X25 did the same thing. And so for another 20 years, we had a protocol where it had retransmission at every node, and we had guaranteed delivery of reliable service. Well, Vint concluded that basically the fibers were going to be so good and were so good that you shouldn't need that, and you could go end to end. The problem is that TCP still depends on that, but distance is killing it because it takes speed of light. and the speed of light won't seem to change very easily. So what we then had was TCP/IP operating the way it is today, and it worked great. Still works great for your HDTV, and so we have something that's really met the test of time. So I met a lot of people now who, for example, are saying, well, we'll just keep on speeding up the network, everything will speed up, everybody will be happier. That's not true, because TCP is now pretty much at its limit. It can do 12 megabits, it can do 15 at times, it can even do up to 30 or 40 in the local area, but it can't do it over any distance. Over 100 miles, forget it. So you're going to be operating maybe at HDTV, but you can't go to 4K TV, which everybody would love to, and you can't go to 8 and 12 and 16K, which are on the table but haven't been, we certainly can't transmit them yet. And you can't do fast backups. You can't do a lot of things that you'd like to do. If we're going to use the cloud effectively, I need very fast downloads. The problem is that can't happen without the network helping somewhat, and the network doesn't provide any help today. So
Or at least not getting in the way.
The concept is the fast routers have to do very little. In fact, that's what MPLS is all about, making it even less than a routing. So in fact, the reality is we do have to do something in the network, and people are doing lots of things. The whole network structure is changing from just routers to lots more stuff. And so that's the thing that people, the carriers and the providers, don't totally understand, that upgrading the trunks doesn't upgrade individual service. So individual service is still blocked by the current structure.
Anything else you want to cover before we open it up for questions?
I'll probably get it during the questions.
Okay. Then
Go to questions. We had some technical problems, and Jeff's slides were not shown today, but they'll be available on our website. That's siliconvalleyhistory.com. Easy for you to remember, siliconvalleyhistory.com. We list all of our upcoming meetings, and for our previous meetings, we have the video recordings, the slides, and sometimes a summary. First, I'd like to thank both Jeff and Larry for this excellent dialogue. Let's give them all a big hand. I'd like to invite questions for either of them based on my nomination and others' approval. Jeff was awarded one of the 3 unsung heroes of Ethernet a couple of years ago, and we're all thankful for that. So feel free to ask him any questions you might have on Ethernet, as this is an Ethernet conference.
And will we have a microphone for questioners?
Where's the
There's one
microphone?
right
Okay, so we're going to come
So
up
I
to
have a question.
where Paul is. I'll get to your question in a second. I just wanted to note that while Larry is quite famous for being the co-inventor or the inventor of the ARPANET, which has become the Internet, he really is also the inventor and the driving force in X25, which was the only public data network of any consequence from 1976 to 1993. Everything else was private data networks. X25 was it, especially in Europe and Japan. So you don't have to restrict your questions just to Internet. You can ask him questions about X25, which was a connection-oriented packet network. Paul, first question.
Fits nicely into my question. Larry, you mentioned packet radio, and I think of the amateur community too, and AX25 and so on. Was there any amateur or hobbyist contribution during those years, or was it pretty much all led by the ARPANET and the other teams that worked on this?
Well, by 71, there was tremendous activity in all sorts of packet-related things, because we showed the ARPANET to the world in a big show in Washington. Everybody started realizing that this was happening. A huge amount of papers got written and done during that period in the community, because we now were understanding packets and Aloha and all of those things, and the congestion issues. So yeah, there was a tremendous amount of work during those periods, but the work on amateur radio didn't happen until much more recently, and is something that is going on nowadays.
Any more questions? Line up and queued. While we're waiting, I'll ask Larry a question, which is a carryover from our lunch discussion. I met Larry in 93, 94, 95 at the ATM Forum, and he was the champion of available bitrate protocol he referred to as ABR. It was a traffic management congestion control and avoidance scheme for ATM adaptation layer 5 packets to provide good quality of service. Here we are 2 decades later, and we don't need any quality of service over the internet. What's going to happen when we have all these streaming videos, not just Netflix and Amazon Prime, but all these packages from Dish Network and HBO and Sony and others offering full motion video, HD, and maybe even 4K with no quality of service in the internet?
Well, I think that is something which can be fixed and needs to be fixed, and it can only be fixed effectively by going into the network and adding some capabilities to manage the traffic at the flow level rather than just at the packet.
So is that the end of TCP?
No,
those
TCP is actually quite functional as a protocol because it works fine for reassembling everything. Everybody's got the routines. It's all effective. What it's not effective at is the congestion avoidance and the recovery. And we need to get the network to help it know more what's the congestion is and to straighten out the congestion. I mean, the user can do nothing about the synchronization of all the traffic on a link, because when one person gets discarded in a router, probably somebody else did. So those 2 start up at the same time, then 4, then 8, then 100. And within a few seconds, everybody is starting at the same time.
So that's an opportunity, great opportunity for innovation in the network.
Yes, there's still tremendous issues that have to be solved for us to go to quality of service and higher speeds for individual flows.
Okay, thanks, Larry. Next question.
Yeah, Nathan Brookwood, Insight 64. I was at Prime Computer back in the mid-'70s, and we were the first commercial mini-computer company to do an X25 implementation. I remember when we announced it to our sales force, I said, hey, we're behind industry standards. And some guy said, well, who else can we talk to? I said, nobody. We're the first guy. That's what we
Well, Data General was there, too. Data General had X25.
Yeah, but we were there first. More important,
Go ahead,
more
your question,
interestingly.
please.
Question, yeah. The question is, looking back, we can see where at key points that when people were designing architectures, they made simplifying assumptions that later came back to bite them, like not having variable length headers in your protocols and so forth. Do you see anything that we're doing now in the networking space or any other space that you watch where there's something that we've done that, 5 years or 10 years from now, people are going to go, boy, that was stupid. Why did we do that?
Great question.
Well, I think the variable length thing is still a valid consideration. We still haven't done much about that. Fixed length addresses are clearly a problem in the future, no matter what we look at. As the networks get bigger and faster, we can handle a lot more going on in the network and a lot more overhead in the packets. So we can do far better. We don't have to compress it to save a bit here and a bit there. We can save, we can use more, and we can do more.
I'd like to take a shot at that, too. I think the big area where we could set ourselves up for trouble or avoid it is in the whole Internet of Things. Whether or not we treat everything in the world that has a gauge in it as a true Internet end station or not has tremendous architectural ramifications. And I don't believe there's any need to do that. I believe that for the vast majority of those things, they can be a local device under control of a local controller, and then you get internet access through that controller, and that controller is a firewall to that device. And there's just an enormous number of macro addressing problems that will avoid over the long haul.
Thank you.
Howdy, Brian Johnsticker, Power Rocks. So I want to ask you kind of a facetious question. I've posed to panels before, but I think the history, experience, and knowledge that's before us makes it a more serious question. So I try and pose it without sounding too ridiculous. But you know, so I kind of joke about, I think of like the Terminator scenario, right? But I mean, at what point with all the intelligence, artificial intelligence, SDNs, right? At what point do you have a realistic prediction for when, you know, that things like the internet stops becoming a tool for us, but maybe becomes something that's so logically, non-emotionally based, that exhibits control, intelligence, and everything that it almost becomes something more defensible than something that's a useful tool for mankind. You know, is that is there a reality to that?
You're talking about the general fear of artificial intelligence getting so powerful that since it's got more neurons than we do, it can start doing things beyond us.
Correct.
Yeah. Well, the internet will help that, but it won't make it happen. It's not thinking. It's moving data around between the systems. But artificial intelligence can do that. Yeah. And I don't know what's going to happen, but I hope people build the right safeguards in.
I think we have to distinguish between software control over a network and its many manifestations versus artificial intelligence. They're really two different things.
Yeah,
there's no thinking. There's no really thinking machine in the internet.
They use artificial intelligence in the data center to manage everything, and it does something. But I don't think it's going to do any more than optimize the network at that point. So it's the medical computer like Watson that may decide that the way to solve us is to kill us. You know, who knows?
Right. I guess it all depends on the definition of optimal, right? But
Yeah.
Thank you.
Okay, next question, please.
Just a quick question. I noticed you just mentioned fixed address network will be a problem in the future. So actually, I was working with Japan NTT and for IPv6 project. So from your point of view, so what do you think in the future the network in terms of IP address? What's your thought about IPv6 and the future picture of IP address infrastructure?
Well, I think the IP address structure is quite effective, and IPv6 gives us enough bits to do that as we choose, although a slightly more complicated mechanism. But the network will keep on growing in speed, and what I hope it will also grow in quality of service and guaranteed ability to move to higher rates, because we will want 16K TV. But it won't work today. One of the problems that people are doing and finding is that with 4K TV, they can't move long distances, so they go to pure just sending UDP rather than TCP and jamming it through the network. Well, the network will collapse if that goes on, if much of the traffic becomes UDP, because there's no control mechanism for congestion avoidance. And we saw that happen in '86. It just died. It just stopped. The network almost went to 2 bits per second in certain links because of the fact that there was no congestion control in the protocol. And when you got to fill the network, which is from '83 to '86, did it, then basically you were winding up with a severe problem. That got fixed. But we've got to do that so that people don't overuse UDP for video transmission. And I don't see them doing that much today, but the 4K people I've talked to are. And that's a real concern, because if it starts becoming 10% of the traffic, we'll all be in trouble.
Thanks, Larry. Last question.
Thank you.
This will be the last question, I think. Lance? Do we have time for more than one question? Okay, then this is the last question, and for those who have other questions, then I think we'll have to take them outside. Is someone else coming into this room, Lance? Okay, so then you can stay into the room, but officially we have to end because there's another session. Last question, please.
Okay, just a follow-up. What about the taking it off the shelf, the stream control transmission protocol? Wouldn't that be a good way to modify the flow control over the network?
Which,
better than
which protocol?
the stream control transmission protocol used in SIGTRAN?
I don't think that it's used widely enough to make much difference at the moment, but the problem with all of the protocols are they're working end-to-end over the network to try and figure out what they're doing, and the network tells them nothing, except to discard packets or delay them. So I think that the problem is the network has to do a little bit more. And ECN actually would have been valuable, but it was never concluded because not everybody did it. There's got to be some coordinated action to fix the network altogether.
Thank you, Larry.
Well, thanks again, all of you, for coming. Let's show our
Thank you, Larry.
appreciations for Larry and Jeff. Great job.